Assalamu alaikum wa rahmatullahi wa barakatuhu, friends. In this video we will discuss VCC resistor, startup resistor or bootstrap resistor calculation. Here we have transformer primary winding. One end is connected to positive voltage of a capacitor, that is called bulk capacitor. The ground end is connected to any MOSFET or any IC. This IC will, when this IC will start switching, it will pass the ground line to this winding. So it will cause to flow electrical current in the primary winding, and it will induce voltage in secondary and bias winding or auxiliary winding or VCC winding. As we know, before starting to any IC, any SMPS controller, any electronic chip, we need a bias voltage, we need VCC voltage. That VCC voltage will energize this chip so it will able to do any function. Here we have VCC pin. For example, if we discuss UC3842, UC3843, pin number 7 is VCC pin. So we need VCC voltage at pin number 7. I am not specially discussing UC3842, 43, any IC. Any IC, I will discuss a generic formula to calculate startup resistor. When we apply power from bridge rectifier, this capacitor will charge. It is called bulk capacitor or main DC capacitor. It will charge at some voltage. What is the voltage level? How much voltage we are applying from input? For example, we apply 220 volts multiplied by 1.414 to take rectified RMS value, it will 311 volts. Or if we have a low line, we can say 85 volt, multiply 1.414, it is 120 volt. So this capacitor, this DC rail will change from approximately 120 volts to 360 volt, 370 volt whatsoever. To take a function from this IC, we need a bias voltage at pin number 7 VCC pin. It is a microchip. It cannot work at 330 volt or 340 volt DC. It needs maximum 28 volts. That is the last limit. So we cannot apply too much voltage directly to this IC. So we have to take a voltage divider or step down converter or any regulator. So we can take a part of this voltage, some portion of this voltage, to give a startup voltage to this IC. So that is called startup voltage. So we need to install a startup resistor here. That is called R startup. When we apply AC voltage, this capacitor will charge linearly. And if we turn on this IC directly when this circuit is charging, there will a surge on the bridge rectifier and filters. So we have to prevent the circuit from surges, from heavy current flow. This resistor and capacitor, RC network, will give a delay start. It will give a delay time to turn on. So here we have VCC and here we have ICC, charging voltage and current. If we discuss this IC UC384243, we have startup current, I startup, that is nominal or typical 0.5 milliampere up to 1 milliampere. So this IC will need startup voltage, that is called UVLO, under voltage lockout. This IC have a special built-in feature. When we apply charging current to this capacitor, this pin, it will charge slowly. Why slowly? Because we will limit the current and we will apply a required voltage at this pin. All voltage will drop on this across this resistor. So it will start charging at a specific rate, that is 0.5 to 1 milliampere. When it will start charging this capacitor, this IC will not work. Its internal circuit, under voltage lockout circuit, will wait until the voltage are reached at a specific voltage level. So it will start charging. The voltage are increasing. Here we have limit that is called UVLO off on. When this IC will reach at UVLO on limit, for example it is 15 volt, at that time this IC will start switching. Before this it was taking just only maximum, we can say 1 milliampere. When it will start consuming 17 milliampere. We have to understand two things. Until 16 volt this IC was in disabled state. It was just only waiting for this voltage. When these voltage are achieved, we can say 15 volt, 16 volt, this IC will start switching. At that time it will start to use this capacitor, because this startup circuit have just only, we can say 1 milliampere. We will limit this resistor, this circuit, to give only 1 milliampere current. The other 17 milliampere will drawn from this capacitor. So this capacitor will start discharging. When it will start discharging and this IC will start switching, it will generate magnetic field. We will receive voltage in secondary and we will receive voltage in VCC winding. This VCC winding is capable to produce the required current here, 17 milliampere. From starting this IC and the receiving voltage from VCC winding, this capacitor will give a backup to this IC. So this IC, if the circuit is good, the output voltage must appear in the output side and the voltage must appear at the VCC pin from this bias winding. So if the capacitor is discharging, when it will discharge, the voltage at capacitor, hold up capacitor, will start decreasing, and this IC is working until here. When it will reach again at this end, the IC will turn off and this will start charging again. When it will charge again until UVLO on condition, upper level threshold, then this IC will start switching again. So it will search the voltage from this VCC winding. So when the VCC winding will provide voltage, so this IC will work smoothly anytime. These voltage are missing, or there is a feedback from the secondary voltage that is provided through the optocoupler. If the feedback is missing, if the VCC voltage are missing, this IC will start reboot, like here. It started to charging this capacitor through main DC rail with a very limited current, that is 1 milliampere, and the required current is 17 milliampere. So when 17 milliampere, when it will consume current from this capacitor, that time these voltage will start discharging. So this hold up capacitor, when it will reach at UVLO lower limit, that is 10 volt or 8 volt, this IC will turn off and it will wait until the capacitor is charged again with this low level current. We can calculate the value of this resistance. As we discussed in UC3842, 3843, the typical startup current, that is 0.5 milliampere up to 1 milliampere. From half milliampere, 500 microampere to 1 milliampere. When we design any SMPS, flyback converter for any universal power supply, the voltage range is normally 90 volt to 245 volt RMS. So a flyback converter will provide the rated output. For example, this SMPS circuit have to provide, we can say 20 watt output at this voltage level or this voltage level. If we are using this voltage level at low line or high line, the voltage must be stable. And when we calculate any SMPS, we make calculation for worst case scenario. At lowest level of the design, the maximum output. For example, 90 volt is the lowest level, low line. So this universal power supply should provide rated output at this level. When we apply 90 volt, multiply it with 1.414, it is 127 volts DC at this capacitor. So we have to use V in minimum, that is 90 volts, 414, that is 127 volts DC. We have 127 volt DC at this line. So we need a current value maximum from 0.5 milliampere to 1 milliampere to charge this hold up capacitor. Using Ohm law, we can calculate the amount of this resistance. R is equal to V over I. Voltage we have 127 volts, and if we use the minimum current 0.5 milliampere, so the resistance value 127 divided by 0.0005, it is 254 K. Now if we use the minimum current 0.5 milliampere, so the resistance value will 254 K. And if we select a mid-range between 0.5 to 1 milliampere, we can say 0.75 milliampere at 127.000075. It is 169 kilo ohm at the rate of 0.75 milliampere. If we use 0.5 milliampere, the resistance value will 254 K. And if we use 0.75 milliampere, it is 169 K. It is our first condition. 127 volts are at minimum voltage, that is 90 volts. As we know, at low line we are taking the maximum output. The circuit will try to draw maximum current from this capacitor. For a very good design, we have to allow a ripple value margin to this capacitor. So we have to exclude the ripples. From 127 volt, we can say it is approximately 15% ripples. We can say 19 volt ripples in the upper level, which will be observed on this capacitor. This is our DC level. So these charging discharging ripples, we can say these will available on the DC capacitor. For a good design, we can select this center value, or we can select this value. If we select this value, our converter will very smooth, without any fluctuation, without any problems. So 127 volts minus, we can say 19 volts that are ripples, it is 108 volts. So we can select 110 volts for a good calculation. This calculation is good, or we can use this calculation. 0.5 milliampere 110 volt divided by 0.0005, it is 220 K. And if we use 0.75, it is 146 K. So we can select a resistor value from 146 K to 254 K in different scenarios. What are that? At 127 volts, if we use the minimum amount, typical amount of current, that is 0.5, it is 254 kilo ohm. And If we use 1 milliampere, the resistance value will decrease. But if we select the value between these two values, 0.75 milliampere startup current, that will more good. It is a good practice. If we calculate these 4 readings and make an average, it will become around 200 kilo ohm. If we add these 4 values divided by 4, because we are taking average for these 4 values, and it will a very perfect range of resistance. Now, when we select any resistance, the resistance is always in ohm, because it will dissipate power, because it have to resist the current. When there is a resistance, there will a power dissipation. We can determine P is equal to I square R, or P is equal to V into I. We can calculate with any formula. We were calculating startup current at the low level, but we have to calculate the power dissipation at high line. What is high line? That is the uppermost limit of the AC line. So 245 volts, multiply it with 1.414 to take a DC voltage on this resistor, on this DC rail, on this capacitor, that is 346 volt. We will consider 350 volts. 245 volt AC RMS, multiply it 1.414, it is 350 volt DC. At high line, we have too much wide range for the voltage, so we have to take the upper peak of the voltage, that is 350 volt DC. When we have 350 volts and we need V into I, 350 volt multiply by amount of current, that is 0.005. If we consider the lower limit, that will 175 milliwatt. 175 milliwatt. And if we consider this current 00075, it is 262 milliwatt. And if we consider this current, that is the maximum current 1 milliampere, in that case 350 milliwatt. For the power dissipation, we have to select the maximum amount of the current, that is allowable startup current 1 milliampere. So 1 milliampere and the highest line voltage, that are 350 volt DC at this resistor. In that case, this resistor will dissipate power 350 milliwatt. To select a resistor 350 milliwatt, we can select half watt, 0.5 watt resistance. 350 milliwatt will much closer to this range. Why? When there are high voltage 350 volt, in that case there is a 34 volt Zener diode inside this IC, that is connected between pin number 7 and pin number 5, that is chassis ground. So 34 volt Zener, it will also use a sink current from this line. This current value will increase. In that case, if the current will increase, it will dissipate power and it will work in the maximum saturation limit of the material. So to prevent, it is recommended to select 1 watt resistance. So if we will select 200 kilo ohm 1 watt resistance, that will the best selection for this startup. If we will select 0.5 watt, 0.5 watt will also work, but at high line, at permanent high line working, there will a sink current, and it will also give a sink current to this Zener, because this line is high, so that time it will continuously dissipate power. And if we select the low level resistance, for example 160k 146k resistance, at high voltage it will dissipate more power. And we can calculate with I square R, with amount of current, that is 0.001 square, multiply it with 200 kilo ohm, that is 0.2 watt, because we calculated at maximum voltage maximum current, that is 0.2 watt. So using 200 kilo ohm resistance and the maximum startup current, this resistor will dissipate approximately 200 milliwatt, but we are selecting 1 watt, that is the good selection. In next video we will discuss a zener. Sometime to prevent this IC, an external zener is connected to prevent this IC. So we will discuss how we can connect a zener to make a protection for this IC. So friends, I hope so this video is informative. If it is informative, hit the like button. If you have not subscribed my channel, subscribe it. Thanks for watching. Assalamu alaikum wa rahmatullahi wa barakatuh.